Hello, I am A.R. Balasubramanian, and in this video, I'll be talking about the parameterized complexity of safety of threshold automata. Okay, let us begin with a very simple distributed computing task. So let's say we have a set of ninjas, and each of these ninjas either want to attack or want to retreat. And the ninjas have decided that they stand a chance at winning only if they all decide to attack. So they will attack only if every ninja decides to attack. And so, if at least one ninja decides to retreat, then all the ninjas will also retreat. Further, some ninjas might be tired from previous battles, and so they might just crash without either deciding to attack or to retreat. How can we model this? Here's one possible formalism. So we have two states, one for each decision of the ninja, and we have two shared variables, that is, variables which are shared across all the process. And if a ninja wants to attack, it can increment the variable at and move to the send state. And similarly, if a ninja wants to retreat, it can increment the variable re and move to the send state. From the send state, there are two possibilities. The first possibility, the ninja checks that the shared variable re is bigger than or equal to 1. And if so, then the ninja moves to the retreat state. And the second possibility, the ninja checks that every ninja has decided to attack. And here n denotes the total number of participating ninjas. And so the check at bigger than or equal to n ensures that every ninja has decided to attack. And so it is safe to move from the send state to the attack state. And finally, from each of these two initial states, we allow the ninjas to non-deterministically move to a crash state. In this talk, we will only restrict ourselves to safety properties. And so a possible safety specification for this task is the following. If we require that if at least one ninja moves to the attack state, then no ninja goes to the retreat state. Okay, so this task we call the unanimous ninja consensus problem because it requires an unanimous consensus in order to attack. Okay, so let's consider a weaker version of the problem. The ninjas have now decided the following, the ninjas have now agreed on the following strategy to attack. So as long as the number of ninjas who crash, which we'll call the faulty ninjas, is less than the number of ninjas who do not crash, which we'll call the non-faulty ninjas, and if all the non-faulty ninjas decide to attack, then they'll attack. For instance, in this case, the number of faulty ninjas is 2, whereas the number of non-faulty ninjas is 3, and all the non-faulty ninjas have decided to attack. So all the non-faulty ninjas will indeed attack. For the other case, it's similar to the previous unanimous consensus problem, where if at least one non-faulty ninja decides to retreat, then all the ninjas will also retreat. How can we model this now? Okay, we introduce a new variable t, which will stand for the total number of processes which are going to crash. And as you may recall from before, n denotes the total number of participating ninjas. And this condition, which we call the resilience condition, is the following constraint. It says that n should be bigger than 2t, which is equivalent to the fact that the total number of non-faulty ninjas, which is n minus t, is strictly bigger than the total number of faulty ninjas, which is t. Okay, and then the basic setup remains the same as before. We have two states, one for each possible decision. We have two shared variables, one for each possible decision. And from the send state, if a ninja checks that the shared variable re is bigger than or equal to 1, then the ninja can move to the retreat state. However, the decision to attack is a bit more complicated. First, we do not allow ninjas to non-deterministically crash. So for this purpose, we have a shared variable f, which will denote the total number of processes which have crashed so far. And before a ninja crashes, it checks that the total number of ninjas which have crashed so far, which is f, is less than the total number of ninjas which are allowed to crash, which is t. And if this is the case, then the ninja is allowed to crash from either of the two initial states, and the ninja also updates the variable f and increments the variable f. As for the attack part, from the send state, before a ninja can move to the attack state, it has to check these two conditions. The first condition is that the shared variable at is bigger than or equal to n minus t. Notice that this check ensures that all the non-faulty ninjas have indeed decided to attack. And the second check is the guard f bigger than or equal to t, which ensures that all the faulty ninjas have indeed moved from their initial states to the crash state. So together, these two conditions ensure that all the non-faulty ninjas have decided to attack, and all the faulty ninjas have indeed moved to the crash state. And hence, it is then safe for a ninja to move from the send state to the attack state. So now the safety specification is the same as before. We require that if at least one ninja moves to the attack state, then no ninja moves to the retreat state. So this task we call the fault-tolerant ninja consensus problem because it tolerates a certain number of faults in order to achieve consensus. Okay. So this example already illustrates all the basic features of a threshold automaton. So in a threshold automata, uh, we, we have states and we have transitions connecting these states. These transitions are guarded by threshold guards, which I'll come to in a moment. So all processes execute the same threshold automaton. Processes are no identities and are hence anonymous. However, what sets apart threshold automata from other distributed computing formalisms like population protocols are the following three features, which I will now elucidate. The first is the notion of a resilience condition. So in a resilience condition, we are allowed to specify variables, which we'll call environment variables, that denote the number of different types of processes executing the protocol. So for instance, in this case, the variable n denotes the total number of processes participating, and the variable t denotes the total number of faulty processes, total number of processes which can crash. And in a resilience condition, we are allowed to specify constraints between these different types of processes. So in this case, the constraint is equivalent to the fact that the constraint is equivalent to saying that the number of non-faulty ninjas, which is n minus t, is bigger than the number of faulty ninjas, which is t. And similar to this, we can have other environment variables for other types of process like Byzantine process, etc. This is the first feature of a threshold automaton. And the second feature is the notion of a shared variable increment. So in a threshold automaton, we have shared variables. So these variables can be accessed by all the processes. And along a transition, a process can increment these shared variables. Now, notice that in a threshold automaton, we only allow shared variable increments and not decrements, as allowing decrements would easily lead to undecidability. So the third and most important notion is the notion of a threshold guard. So in a threshold guard, we are allowed to compare the current value of a shared variable with an affine linear combination of the environment variables. So in this guard, we are checking if the current value of the shared variable at is bigger than or equal to the value of the expression n minus t. And a process can take we say that a transition is enabled only if all the guards of the transition are true at that particular point, and a process can move from one state to another by a transition only if that transition is enabled at that particular point. So these three features are what set apart threshold automata from other distributed computing formalisms. Now that we have seen a brief introduction to threshold automata, I will now describe the sort of problems that we are interested regarding this. So given a threshold automaton, so as I had mentioned before, since all the processes executing the threshold automata are anonymous, the complete picture at any given point in a run is determined by the total number of processes in each state, the values of the shared variables, and the values of the environment variables. So these three pieces of information together is what I would call a configuration. Now, the sort of problems that we're interested in are as follows. So we are given a threshold automaton, and we are given two sets of states, which I will call q bigger than 0 and q equal to 0. So these constitute what I call a specification. Given a threshold automaton and a specification, we would like to verify whether there exists a population size n such that running n copies of this threshold automaton satisfies the specification. So what do I mean by this? I mean that running n copies of this threshold automaton will reach a configuration which puts at least one process in each of the states in q bigger than 0 and exactly 0 process in each of the states in q equal to 0. So if this happens, then I say that the given automaton satisfies the specification. So this is what I call the safety verification problem. And it is known that the safety verification problem for threshold automata is NP complete. So in this paper, what we do is the following. We find parameters of the input, which are usually small in practice. So what I mean by this is the following. So it has been observed in practice that the resilience condition for threshold automata is usually very small. It usually contains constraints of roughly 5 or 6, of roughly size 5 or 6, and hence the size of the resilience condition is a potential parameter which is usually small in practice. And what we would like to do is we would like to find fixed parameter tractable algorithms or FPT algorithms. So what I mean by this is that I would like to find an algorithm for the safety verification problem such that it runs in time f of k times a polynomial in the input size, where the function f solely depends on the parameter k. The hope is that if the parameter k is small in practice and f is a moderately exponential function, then we can still feasibly solve a safety verification problem for threshold automata in practice. Alas, what we show our main result regarding this problem is a negative result, which which is as follows. So we take our we take as our parameters the number of distinct cards appearing in the threshold automaton, the size of the resilience condition, the size of the specification, and the maximum constant appearing in any of the guards of the threshold automaton. With these four things as parameters, we show that the safety verification problem for threshold automata is W1 hard. So roughly W1 hard is the parameterized equivalent of NP hardness, and it is widely believed that no W1 hard problem has an FPT algorithm. Okay. Motivated by this, we consider two restrictions for which we provide FPT algorithms. So the first thing that we consider is threshold automata with an acyclic control structure. And for these automata, which we call acyclic threshold automata, we show that the safety verification, when parameterized by all the four parameters that I had mentioned before, along with the length of the longest path in the threshold automaton. So for safety verification parameterized by all these five parameters, we indeed have an FPT algorithm. This is our first positive result. And our second and more important positive result is as follows. So we consider a restricted class of threshold automata, which we call multiplicative threshold automata. And for these threshold automata with constantly many fault guards, I'll explain what both multiplicativity and fault guards mean in the next section, but for now I'll just state the result. So we show that for this restricted class of threshold automata, there is an algorithm with running time f of size of the number of guards times a polynomial in the input size. So this g here denotes a number of distinct guards appearing in the threshold automaton, and this f is a function which solely depends on this g. Due to lack of time, I'll only explain the main idea behind this last result. Okay, before I move on to present our main result, I had promised to define what multiplicativity and fault guards mean, and so I will do that by means of the running example that we have. Okay, so we have a threshold automaton, and of course this threshold automaton has threshold guards, which I will now group into two types. So if a threshold guard contains a greater than equal to, then I'll call those guards rise guards. So for instance, the guards at bigger than or equal to n minus t, f bigger than or equal to t, and re bigger than or equal to 1 are rise guards. And similarly, if a threshold automaton contains a less than symbol in it, then I will call it a fault guard. So for instance, in this case, the guard f less than t is a fault guard. So this defines what a fault guard is, and now I'll define what multiplicativity means. So multiplicativity roughly means the following. So if x is a solution to any of the constraints in the resilience condition or to any of the guards, then multiplicativity requires that mu x is also a solution to that corresponding constraint in the resilience condition or to the corresponding guard for every natural number mu. So as long as x is a solution, then mu x should also be a solution. For example, let's take this guard at bigger than or equal to n minus t, and it's easily seen that if at is bigger than or equal to n minus t for some concrete values at n and t, then mu times at is also bigger than or equal to mu times n minus mu times t. In fact, it can be checked that this threshold automaton, but as a whole, satisfies the multiplicativity property. Okay. So now, how do we solve the verification problem for multiplicative automata with constantly many fault guards? Before I describe the solution to this problem, I need to justify these restrictions, and the easiest way to justify this is that a majority of the protocols, majority of the threshold automata occurring in literature satisfy the multiplicativity property and have at most one or too many fault guards. A more detailed justification of these two restrictions is given in the paper. And for now, we just concentrate on describing the solution to this problem. Okay. So before I describe the solution to the safety problem, let us consider a restricted version of the safety problem. On this restricted safety problem, we are given a threshold automaton. We are also given a specification as before. And additionally, we are given a subset of transitions, RS. So in this case, we have removed this transition between the states sent and attack, and we have retained all the other transitions. And this subset RS is now the set of all these 5 transitions that we have here. And in the restricted safety problem, what we want to check is the following. We want to check if there exists an initial configuration sigma, which can reach a configuration tau, with tau satisfying the given specification. Notice that this part is the same as the usual safety problem. And additionally, we want this to satisfy two conditions. So we want that the run between the configuration sigma and tau uses exactly the transitions from the subset RS. This is the first restriction. And the second restriction is that we want the configuration sigma and tau to satisfy all the guards in all the transitions of RS. So for instance, in this case, we want a configuration sigma and tau to satisfy the guard f less than t and also the guard re bigger than or equal to 1. Notice that these two are what set apart the restricted safety problem from the safety problem. And our main contribution is a polynomial time algorithm for deciding the restricted safety problem. And later on, we'll see how this translates to an FPT algorithm for the safety problem. Okay, so we will now impose two relaxations on the usual transition relation of a threshold automaton, and we will then observe that these two relaxations do not alter the answer to the restricted safety problem. Okay, so the first relaxation is that we allow fractional firing of transitions between configurations. So let us recall the usual transition relation between configurations. So a process in some state can pick a transition which is enabled at that particular configuration and can fire this transition to go to a new state, right? And along the transition, it increments the shared variables that it encounters. This is the usual transition relation. For instance, let us consider the configuration which has one process each in the red ninja state, the blue ninja state, and the send state, with the shared variables at being 0 and d being 1. So let us consider the process in the red ninja state, and this process chooses the transition which allows it to move to the send state and increments the shared variable at. And so the new configuration that we get is one is the one where there is one process in the blue ninja state, two processes in the send state, and the values of at and re are both 1. This is the usual transition relation. And now we introduce what we call the fractional transition relation. So in this transition relation, a process can choose a transition which is enabled at that configuration and also choose a fractional value between 0 and 1. So in this example, the process in the red ninja state has chosen this rule and has also chosen this fraction 2 by 3. Once it has chosen this fraction, it can split itself into two fractional copies. So for instance, in this case, the process in the red ninja state splits itself into one copy of size 1 by 3 and another copy of size 2 by 3. And what now happens is that the copy of size 1 by 3 stays in the red ninja state, and the copy of size 2 by 3 uses this rule to move to the send state. So this is what we have denoted pictorially by having 1 by 3rd fraction of the red ninja state and 2 by 3rd fraction of the send state. And since only 2 by 3rd of the fraction of the process of the red ninja state went to the send state, the shared variable at is also incremented to only 2 by 3rd and not to 1. So this is what we call the fractional transition relation. Notice that the fractional transition relation is a relaxation of the original transition relation. So now we can define a fractional reachability relation in the obvious way, which we denote by this notation. And what we prove is that due to multiplicativity, if we have a fractional run between sigma to tau, then there is a natural number n such that from n copies of sigma, we can reach n copies of tau using the usual transition relation. By nature of specification, tau satisfies spec if and only if n times tau satisfies spec. And due to multiplicativity, sigma and tau satisfy all the guards in RS if and only if n times sigma and n times tau satisfy all the guard in RS. And hence, by putting all this together, we observe that to check the restricted safety problem, it suffices to check if there exists a fractional run between sigma to tau with tau satisfying spec and sigma and tau satisfying RS. The second relaxation is more drastic, and it proposes to remove all the guards from the transitions in RS. A priori, it sounds like this is an unsafe thing to do, but we actually consider the following fact. So let's say we have a fractional run between configuration sigma and tau, and let's say sigma dash is some intermediate configuration. And assume that we are guaranteed that sigma and tau satisfy all the guards of all the rules of RS. Now, since shared variables can only increment, the values of the shared variables in sigma dash are sandwiched between the values of shared variables in sigma and the values of shared variables in tau. It follows that if sigma and tau satisfy all the guards of all the rules in RS, then sigma dash also satisfies all the guards of all the rules in RS. Hence, if we are guaranteed that sigma and tau satisfy RS, then we don't have to necessarily check that every configuration in between also satisfies all the guards. And hence it suffices to check that in the unguarded version, that is in the version where we remove all the guards from all the transitions in RS, if there exists a fractional run between sigma to tau with tau satisfying spec and sigma and tau satisfying RS. Now, putting these two observations together, we have the following. So we notice that unguarded threshold automata are simply petri nets where the states are the places and the transitions are the transitions between these places. But this by itself means nothing since reachability in petri nets is notoriously hard. But what we show, but it is known that reachability under fractional firing in petri nets can be solved in polynomial time. So this is a fact which is known about fractional reachability in petri nets. And using this fact and additional tricks and observations 1 and 2, we show that the restricted safety problem can be solved in polynomial time. And this is our main contribution. And now that we have solved the restricted safety problem, how do we solve the general case of the safety problem? Using previous results on threshold automata, what we show that solving a safety problem can be accomplished by solving these many restricted safety problems, where G denotes the number of distinct guards, R denotes the total number of transitions, and GF denotes the total number of distinct fault guards. And so notice that if GF is constant, then this value is of the form f of G times a fixed polynomial the size of the input. And since we had already shown that solving restricted safety problems can be done in polynomial time, it then follows that if GF is constant, then the time taken to solve the general case of the safety problem is of this form, and hence is fixed parameter tractable in the total number of distinct guards that appear in the threshold automata. Okay, and this completes the theoretical part of our contribution. So we have implemented this algorithm that we have just described on various threshold automata obtained from various distributed algorithms from the distributed computing literature. And we have also compared it with two other algorithms. So BiMC is a state-of-the-art model checker for checking various properties of threshold automata. And we also cross-checked our algorithm in this paper with the algorithm used to prove NP completeness of the safety verification problem. And we observe that there is no clear winner in the sense that there are cases in which the algorithm in this paper performs worse than the other two algorithms. And there are cases in which our algorithm performs better than the other two algorithms given in the paper. Hence, we believe that our algorithm is not just theoretically interesting, but also interesting from a practical perspective. To conclude, we have shown that verification of threshold automata is hard, even from a parameterized perspective. And so we have identified two restricted cases for which we were able to provide FPT algorithms. And we also implemented these two algorithms, and an empirical evaluation of these algorithms suggests that it can have good practical performance as well. Thank you for your attention, and I'll be happy to take any questions.